Welcome to the next part of Chapter 18 on electric charge and electric field. In this section, we're actually going to introduce the concept of electric field. And to motivate that discussion, we're going to begin with going back to the last example we did in the last part, which is here, where we found the net force on the 4 Coulomb charge. And in that process, we found that the net force equaled 1.3 times 10 to the 11th newtons. And the angle it made was 86 degrees, and that was below the axis. So F net X went this way, F net Y went downward, and this is that 86 degree angle. Remember all the work we had to do to get that answer. It was 4 or so slides worth of calculations and manipulations. And now what I want you to think about is, what if I replaced that 4 Coulomb charge? What if I replaced it with a 2 Coulomb charge, or a negative 5 Coulomb charge, or a 6 Coulomb charge? What if I wanted you to do all 3? And hopefully now you're looking at me like I'm crazy and how, that math was horrible. How could I ask you to do it again? If you go back and look at that math, we used Coulomb's law 3 times, one for each of the other charges. And so we had things like F negative 1,4, which was K times 1 Coulomb times 4 Coulomb divided by whatever distance that was squared. I don't remember what it was, so I'm just going to put parentheses and put a square and say I know there's a number there and I forget what it is. And if I go and I look at one of the other Coulomb's law things, Coulomb's law applications that we did for the last example, all of them were multiplied by 4 coulombs. So really, what I need to do to switch from a 4 Coulomb charge to a 2 Coulomb charge is take this, divide by 4 coulombs, and multiply by 2 coulombs. And if I want to switch from 4 coulombs to negative 5, I would divide by 4 and multiply by 5. And same thing for the 6. Okay. So now I want you to think about a version of Coulomb's law, which looks like this. Okay, well, I got rid of the subscript 1 and 2, and why did I do that? I replaced it with S and T. Well, QS is going to be the source charge. It's going to be the thing that stays the same. So if I look at the negative 1,4 above, the source charge would be the 1 Coulomb. The other one would be QT, is the test charge. That would be the 4 Coulomb in the one above. Or it could be the 2 Coulomb, or it could be the 6 Coulomb. And now I'm going to redefine or make a definition. And what I'm going to do is I'm going to link this piece together. And I'm going to give that a name because I'm going to be using that over and over and over in this process. And the name I'm going to give that is the electric field. And then I multiply it by the charge that I'm placing in the field to see, hey, what is the force doing on that particular charge? Okay. Often you'll see this written instead of that way. Usually it's rearranged to be F equals QE. And E by definition is K times a charge divided by R squared, where this charge is the thing that is causing the electric field at that point. It is the charge that stays the same no matter what I do. And I should clarify that this version of the electric field formula is specifically for point charges, but that's all we're going to be dealing with in this class, so it'll be perfect for our needs. Okay, so what does the electric field do? It represents the direction of the electric force on a small positive charge. And I'm going to put this out there. It is the force on a small positive charge. So if I think about having a positive charge here, and I think about bringing another small charge that is positive and sticking it here, it's going to be repelled. So the electric field out of this positive source charge would point out at every point. On the other hand, if I had a negative charge, and I think about bringing another small positive charge in there, it will be attracted. So the electric field due to a negative charge will point the opposite direction. Not only that, but if I actually did bring a positive charge in here, it would follow the field line. So the force on a positive charge would be away. I'm going to put a little plus sign there. But if I were to bring, and I'm going to clarify that because my eraser is not working. Okay, hold on. We're just going to scribble this out. Why don't I like it? Because technically at that point, that's not how the force would go. It would go off at an angle. If I take a symmetric point over here, the force should point this way. So if I bring a positive charge in, the force is going to push it away, so it'll be outward everywhere. But if I were to bring a negative charge in, the force would be inward. So positive charges are going to move with the electric field. Negative charges are going to move against the electric field. So, by convention, electric field lines point out of positive charges and into negative charges. We just discussed that. The number of field lines that start or end on a charge is proportional to the size of the charge. That's something we will see here in a minute when we pull up that simulation. And the closer the field lines are, the stronger the field is, which we will also see on that simulation. Now, this simulation runs in Java, which may or may not work on your computer. And for that, I'm sorry, but it really is better than most of the other ones I've seen. So I still use it for that reason. When you pull up the simulation, you will see something like this. It does usually have a couple more of the boxes here on the right checked. I've unchecked them so that all we're looking at is the electric field. Now, this simulation does not use arrows to represent the direction of the field. Instead, it color codes. So negative charges are blue, positive charges are red. Right now, I have it set to give me a positive charge of 9. Maybe it's 9 coulombs. I don't know. There's no units there, but we'll go with it. And that does this. And so it does point radially outward, as I said it should on the last slide. Okay. And we can see there are a ton of lines here. I'm not going to bother to try to count them. If we reset and go for a smaller positive charge, here's a 3, you can see same basic shape. It still looks like all the lines are going radially outward, but there are fewer of them, indicating that this is a smaller charge. Okay. If I go to a negative charge, let me reset. The negative 9 looks exactly like the positive 9. If you actually did pause the video and count all the lines, you would get the exact same number of lines. At least you should. Which shouldn't surprise you, because the only thing that differs from a positive to a negative charge is the direction. Okay, one other thing that was in the last slide was that field lines are closer together where the field is stronger. Remember that if I were to bring a little charge in and bring it closer to the source charge, stick it here, it would have a much bigger force on it than it would out here. Here the lines are much more closely packed together than they are out here, indicating the stronger field. Okay, well, one charge is great. I'm going to get rid of that one so I can move it over. But two charges is even better. So here we have two like charges. They're both negative. And we can see there's this weird spot in the middle where all the field lines are trying to avoid each other. Why is that happening? Well, if you think about bringing in a little positive charge and sticking it smack dab in the center, it's going to be attracted to this guy on the left, and it will be attracted to that guy on the right. And since those two charges had the same, were the same size, those attractions are going to be equal and in opposite directions, which means the net force at that point in the center will be 0. If I don't use balanced charges, so I start with a -9 and go with something smaller and negative, I still get a place where the field goes to 0, but it's no longer centered. It shifts towards the smaller charge because you have to be closer to the smaller charge in order to account for the fact that the charge is smaller in Coulomb's law. If I switch to positive charges, I get the same behavior that I saw with the negative. Again, shouldn't be overly surprising. If I go with one positive and one negative, I get something different. If we again think about what is happening here in the middle, if I put a little positive charge down, it's going to be repelled by this positive source charge and attracted to that negative source charge. So it's going to get pushed by the red and attracted to the blue, and it's basically going to go zipping across. Again, assuming it's a positive charge that we're putting in. Negative charges would move the opposite direction. Okay. I can also do fun things, like if I put in, I'm doing my best to get this, but I'm not doing very well. And you can see that it's starting to struggle with creating the field. But when I make a line of charge, you can see on the edges this doesn't hold, but in the center the lines are almost getting parallel to each other, which is really important, and we'll discuss why for that here shortly. I'm going to reset this. These patterns can get very complex and very pretty, so I'm going to just pull up one here. We can look at it and we can make some conclusions. For example, if I couldn't see that this one was blue and that one was red, I would know that they had opposite charges. The charges had opposite signs because I could see that the lines are connecting. As opposed to this one and that one where I do have that null forming in the middle. Same thing here. I can tell that this is a smaller charge because it has fewer lines. I can tell that the field is stronger here than, say, over here where the lines are further apart. I can look at this and determine a lot about what's going to happen. Okay, so I think that is everything here. Field lines point out of positive into negative. Number of lines starting or ending on a charge is proportional to the size of the charge, and the closer the lines are, the stronger the field. Can electric field lines cross? Okay, well, with the exception of when I tried to do the line and things started not plotting quite correct, okay, all the other ones, did you ever see that happen? Well, let's think about what that would mean. Let's say I have two charges and this one puts out a field line and it does this, and this one puts out a field line, and there they are, they crossed. Yay! And now I take an additional charge and I stick another little test charge right here. So T for test, this is a source charge, that is a source charge. Remember, the electric field is supposed to tell you the direction of the net electric force on a test charge. But I have two possible directions for the net force. Let's assume both of our sources are positive, so the field lines point out. Which one's correct? Okay, so the problem here is no. We can't have field lines cross. And the reason for that is because each point only can have one net force. here I would have two net forces. Well, if I have two net forces, then I haven't figured out my net force correctly. Okay, really quick, I'm going to draw some of the basic field that you might see. So if I have a single positive point charge, I get field lines pointing out everywhere. If I have a single negative point charge, then field lines point in everywhere. These two, since they both have 4 lines, we can assume that they are the same size. Isn't that convenient? If I have a positive and a negative charge, then the field line points out of the positive and into the negative, and we do typically get this wrapping effect. And on the other side, it does something like this. And if I have two charges with the same sign, in this case it's positive and positive, then I get the field lines point outward everywhere, but I get this weird null where the field goes to 0 because the net force on a charge at that point would go to 0. Okay, lines of charge. I tried to show you this, and the simulation had a little bit of trouble. And what I really want to focus on is the middle area, not the ends. And I'm going to redraw this to simplify it. And again, my eraser's not working for reasons I don't know, but that's okay. We will just get rid of that. Easy peasy. Okay, so here's my line of charge. Let's let this plate be a positive plate. So the field lines, not near the edges, will point outward everywhere. Now what's really, really cool is if I take and put a second line of charge with the opposite sign, then those field lines basically extend all the way across. And the nice thing is that the field in between our two lines of charge, the field in here, is constant. Meaning the magnitude is constant and the direction is constant. Which means if I were to toss a little charge in there, the force on it would be constant, which means its acceleration would be constant. And as soon as its acceleration is constant, I can use the kinematics equations that we learned in the first part of the first semester to determine what the motion of that charge is going to be between those two plates. And that's pretty darn cool. Okay, so next thing, inside and outside a conductor. So I have a conductor. In this case, let's assume it's a plate of copper. This plate of copper has some positive charges and it has some negative charges. And if it's neutral, those two balance each other out. And remember, as we discussed in the last part, the positive charges are stuck in the nucleus and they can't really move. So we're going to move the negatives around. So what happens? We put this conductor in a uniform electric field. So if it's on this side, it's also on the other side. Okay, what does that electric field do? It puts a force on those charges. Now remember, the positives are kind of stuck, so we're going to wiggle around the negatives. So what are the negatives going to do? Well, as we've discussed, the negatives move opposite the electric field. So the negatives are going to try to move this way. And they are going to move and rearrange themselves and shuffle themselves around until they have no net force on them. Okay, there are two things contributing to the net force. One is that external electric field. The other is the repulsion they feel relative to each other. So they're going to wiggle until they get no net force. And the repercussion of that, the repercussion of them moving until the net force, oops, let's try that way, F net equals 0, means that the electric field inside is 0. The electric field that is formed by those negative charges in their new configuration exactly cancels out the external electric field that that conductor is sitting in. Okay, so let's go look at an example of this. And that example is a Faraday's cage. And I've got a link to a video here. I'm not going to show you the entire video. I will, however, pull it up and show you just a little bit so you can see what's going on here. Oop, maybe. I'm trying. Here we go. Here is the video. I've actually moved forward a little bit through it. So let me describe what you're seeing. We have these two kind of mushroomy things. Those are Tesla coils. And Tesla coils are a great way for creating a large charge separation. Okay. You can also see there's a guy in the background here. That guy in the background is a musician. And that musician's instruments and microphones and whatnot are connected to the Tesla coil, causing it to create these charge separations. You also have a cage in the front. And in that cage is a gentleman, and you may know him. That is Adam Savage, who's one of the Mythbusters. If you don't, well, that's Adam Savage. There you go. Now you know. So what's going to happen? The nice musician is going to play his music. Not my favorite type of music, I must admit. Maybe it's yours, which is okay. He's going to play his music. That's going to cause a charge buildup. Charge buildup happens, much like static electricity in your home. Eventually, the air starts conducting, and you get a spark, a lightning bolt that goes from the Tesla coil to the cage, where Adam Savage is gainfully standing right now. And he's perfectly okay. He has nothing to worry about, unless he would to make the mistake of touching the cage. But he does not do that, so we don't need to worry. So hitting play. So you can see he starts dancing and perfectly safe. Okay, that's enough of Adam Savage in a Faraday cage. Okay, so not all of us have Tesla coils laying around connected to instruments and cages that we can just stand and dance in. So a more practical application of this is your car. The inside of your car is a Faraday cage, so that if lightning strikes your car, you at least are safe. Now, there are connections to the electronics of your car and all sorts of other things that could potentially be fried because they are connected to the Faraday cage in order to make the electric system in your car work. But you yourself are safe because you're snug inside and not touching that cage, which is pretty darn snazzy. Okay. This is a little bit of a quiz. If you want to stop and think about it before you hear me give the answers, that's perfectly okay. What you see here are a collection of 4 charges, 2 positive, 2 negative, and 3 marked locations, A, B, and C, which I said in one order and circled in the other. Okay, and the question I'm asking is, where is the field biggest and, ooh, there's a T needed there, biggest and smallest? Okay. Well, hopefully you look at this and you say, oh, look at A. A is sitting in one of those nulls between 2 charges. So at A, the field has to equal 0. If I look at B and C, at B, the field lines are closer together in general than they are at C. So point B has field lines close. So that's going to be the biggest. And C is going to be somewhere in the middle. Okay. The other thing that I ask frequently with this is, which charge is biggest? And I'm just going to jump forward a slide and show you the answer to that one, because it's actually a bit of a trick. You count the lines, what you realize is this positive and that negative had the same number of lines, therefore they were equal, and the same with the other two. Okay, this concludes this part on electric field. In the next part, we're actually going to do calculations associated with the electric field.